All right, so let's get started. Today is one of my favorite days. We're talking about calibration methods and techniques, and we're going to start with what you did in quantitative analysis and any of the other labs, probably instrumental, where you use external standards, build a calibration curve, then do an unknown, etc. But then we're going to expand that to internal standards. Maybe, I don't know if you've used internal standards before. You have? In what situations?
We run internal standards with some of our trials in Petrokovic's.
Oh, in Petrokovic's lab. Yeah. I was wondering about in the curriculum, like instrumental or.
We run it in.
You did. Okay. Well, good. So we're building on that background, and then we're also doing the propagation of uncertainty for all of those, and using that to explore the changes in precision and accuracy as we go through. And then we're ending up with standard editions. And so we'll cover all three of those today, if I stay on track and don't get too sidetracked. And then we'll talk about, because in forensic science, you're going to have a lot of variety of matrices. You know, you might have blood serum, or you might even have like the fluid in the eye, or you've got urine samples. You've got a lot of complex matrices. Now, most of those are aqueous solutions, but there's active agents in there, specifically enzymes. And so a lot of those enzymes are still active, and they're still doing chemistry over time, even though the body's dead. So you put blood in, or you put a drug in a blood sample, the enzymes there, even though that blood's not being oxygenated and flowed through the body and filtered in the liver and so on, there's still enzymes in that blood serum, and they're still chewing up your analyte. And so that's kind of what we see here in some of today's results. So it'll be interesting to look at. So this is all about sort of predictive modeling and calibration. We're setting up a calibration curve to kind of predict the behavior of an analyte. And then we pulled our samples into that model. And so this is I guess the term that I really want you to be comfortable with is anytime you fit a line to a set of data, you're making a model. And the reason you want to put a line in there is because a line fills in all the gaps. You maybe have 5 data points, but then that line is infinitely variable. You can find a data point anywhere on that line. And so you've got a model now for the behavior of the analyte. And so we have the dependent variables and independent variables. The independent variable in almost every situation is your concentration or your abundance. Now, a few years ago, I used concentration all in this talk, in this lecture, and then on the exam, because of the example that I used out of the book, it used the word abundance, and that totally destroyed the students' grades because they didn't understand what abundance was. It's the same thing: concentration, abundance, amount of material. And there's a bunch of different units for that. There's molarity, milligrams per liter, parts per billion. All of those are abundance. Okay, and those are your independent variables. And then the signal depends upon that. And so that's your dependent variable. So whatever signal you're using, it could be area counts under a peak, like in GCMS. It could be absorbance, if it's atomic absorbance, or FTIR, infrared absorbance, UV-vis absorbance. Extinction coefficient, you might have that also if you were to figure out if you were able to pull out the concentration variable and the length variable and so on, you could be left with that extinction coefficient in terms of the Beer-Lambert law. So there's a lot of different signals that you could have, and there's a lot of different concentrations or abundances that you could have. But you just always look at the units that you're using and try to understand what that model is calibrating. In today's examples, we're looking at area counts on a chromatogram. And then along the x-axis are independent variables, parts per billion of cocaine. Now, we try to judge our calibration model in terms of its usefulness. And one of those factors of making it useful is that it covers a large dynamic range. Then we typically call this, or refer to this large dynamic range or linear dynamic range in terms of orders of magnitude. So how many powers of 10 does it cover? Today's calibration models cover quite a large, have quite a large linear dynamic range. And so orders of magnitude is just powers of 10. Just look how many place values go from your minimum standard to your maximum standard. So on the y-axis, you could just look to see how many place values are on that y-axis. Does it go from 100 to 100,000? Then there's a change in 3 place values from 100 to 100,000. Then it's got the 3 orders of magnitude in terms of its linear dynamic range. Then we have the limit of quantitation, the LOQ. So this is the smallest significant concentration in the linear dynamic range. So there's a bunch of words packed in here. This is a concentration value. You can also have a LOQ signal, so the amount of area, but you're going to convert that over to a concentration or an abundance. So this is really on the x-axis. What's the smallest significant concentration that you, when I say significant, I mean statistically significant. So you could defend an answer at that point and higher. Below that point, you can't really defend it. And then we have the limit of detection. Now this is a signal value. So this is the y-axis. It's the smallest significant. And when you see significant, you think statistically significant signal above background. So you're going to have noise in your chromatogram. You can integrate noise. You can come up with area counts even if there's no peak. So that's going to be your background. And what's the smallest peak that you could be confident in? Right? If you have an area count in your noise 1,000, rule of thumb is 3 times your background would be the smallest significant signal. It's just a nice rule of thumb. It's like 3 sigma, right? So if your background gives you 1,000 counts between these 2 limits, even though there's no peak there, you'd have to have a peak that gave you an overall value of 3,000, 3 times your background before you can say, all right, that's a real peak. That's a significant signal. You might not be able to quantify it with like 95% confidence, but you could say there's a significant signal there. And so if you're doing this, you can't ever say there's nothing there. You can just say it's below detection. All right. So if you see a little bump there and you integrate it and it's 2,000 and your background is 1,000, you just say it was below our detection limit. You can't really say there's 0 there. You can't really test for 0, but you can say it wasn't significant enough for us to be confident that we detected anything. So we just say it's below detection limit. One of the worst things that legislators can do is to hear about the method's limit of detection and say, well, we're going to set the law at that. So we're going to say, we want safe drinking water. And so we find out that the drinking water test has a limit of detection, actually probably should be LOQ, a limit of quantitation as like 3 parts per million of arsenic in drinking water. So we're going to set the regulation at 3 parts per million. And that is terrible because you really can't control something down to your limit of quantitation. That's the very first time you can be confident that you've seen anything. And so essentially they're saying we don't want any arsenic in the water, when to take something down that low would be not cost effective and really not necessary. This happened to a city in the panhandle of Texas when I worked up there. They had just natural, their drinking water had arsenic in it, not a dangerous level, but it was definitely quantifiable. And then there was a regulation that came down for water release into creeks and rivers and so on. So this environmental regulation came down that set the arsenic level below the safe standard for drinking water. And so what they were in the situation of, we could drink this water, but in order to release it, we had to treat it. Because the safe level was here, but the release level was here. So there was, again, these environmental regulations, when they get into these limits of quantitation, can really get upside down. And it takes smart legislators to kind of look at the totality of the situation. Then we have another figure of merit, the correlation coefficient, which we've already talked about. We'll talk about some more today. That is sort of the percent of the model, the percent of the scatter in the data that's covered by your model. And your model doesn't have to be linear. It could be quadratic. It could be, any polynomial fit essentially. And this would be the amount or percent of scatter in the data that's captured by your model. Now, there are a lot of other sort of analytical pieces to the puzzle. Just get that chat out of the way so you can see. Like there's blanks where you run your matrix through, but it doesn't have the analyte. You have controls, so these are known amounts that you run through your calibration curve just to check to see if the situation of your instrument and your procedures have changed over time. There's blind controls where if I'm doing an analysis and checking my own calibration, then I have you make one up, and then I check my work with yours, and I don't know what the concentration is, and so then I would calculate the concentration and give it back to you. There's calibration checks where I put in a known concentration at different places in my model and see if it hits the line or not. Then there's replicates and duplicates. Replicates are starting with like doubling the analyte and making a replicate sample with the same concentration. A duplicate is at the end, just splitting that one and duplicating that. So it's one prep, two runs, and a replicate is two preps all the way through. And then a spike is taking an unknown and spiking it with known. So I'm adding more of the analyte to a particular sample. Now that's really handy if you have an unknown that appears to be really low, and you think, well, maybe this comes down below the level of my confidence in my calibration. I can spike it to pull it up into the middle of my calibration curve. If I spike it with a known amount, I haven't really screwed anything up because it still has the unknown amount and now the added known amount. And so it's still I can take the amount I added out and know what was already there. So that page 70 refers to the second edition of the Bell book. So I've got a library copy if you want to read more about those things. I'm just really calling out those different figures. Let's get into calibration and understanding some of these calibration models. So here's a horrible calibration curve, but it's a good one to show you all of these parameters that we talked about. We have the limit of detection down there, which is 3 times the blank value. And then I've seen limit of quantitation listed a whole bunch of different ways, but one of the talks, and it was one of the PhD talks in forensic science, downstairs, or actually from now upstairs from here. And they were using a limit of quantitation as 10 times the blank value. Okay, so that's pretty generous, but they wanted to make sure that they were statistically confident in their LOQ. So we can use that as again, a rule of thumb, but your particular lab will have policies associated with what you're going to use. What do y'all use, do you know, for Petrokovic's lab?
There's some kind of formula.
Okay.
10 times.
But it is a factor of 10. Okay, so it's
LOD was 30, I think.
Okay. And so yeah, so in next week's homework, we have you calculating all of these values, okay, on a data set. And so I have you do the limit of detection as 3 times and the limit of quantitation as 10 times. Okay. And then hopefully, when you go 10 times above your noise level, you're going to be in the linear range of response. And so from that point up, your model should be somewhat linear. You double the concentration, you double the signal. You half the concentration, you half the signal. So you're in a linear range of response. But if you go too far and you get too concentrated, I can't think of any signal that doesn't saturate. Like if your peak grows and grows and grows and you're adding more and more concentration, eventually your detector can't respond anymore. And so then those peaks get flat. And so if you see up here, like in this region here, a tiny concentration will have a tiny peak, and a larger concentration will have a larger peak, and the saturation will have a flat peak. Something like that. And so we're missing this signal. You see that? So our detector just can't do it. And so that's why it tapers off. So now we're totally flattening the tops of our curves, and we're not going to get any more signal out just by raising the concentration. And so that's what we mean by saturation. And I say this is a horrible calibration curve because look at these data points. They're just awful. Look at that, you know, they're off the line. In this range here, if you just use those standards, you'd have a completely different model. It's a much more gradual slope. Okay. And so this is going to have a pretty crummy R squared value. You know, like it might still be 0.9, but it's probably not 0.99. You know, it's going to be 0.91, maybe even in the 8s or 7s. And again, we're in chemistry, and our models a lot of times have 2 or 3 9s in the R squared. That's unusual for most statistical analyses. I was doing the correlation of my student evaluations when I was at West Texas A&M, correlated with the class average. So if class average went up, my evaluations went up. Class average went down, my evaluations went down. And I had a 0.7 R squared. So 70% of the evaluation score was just how good the class on average did, right? Which kind of makes some sense. And I told my neighbor who taught meat science and did work on the tenderness of ribeye cuts and beef and cattle, depending upon their feed. And I said, but the R squared is only 0.7. And he says, I'd give my right arm for an R squared of 0.7 in his studies. You know? And so we're spoiled in chemistry because we have everything locked down, the instruments, the solvents are clean and all that stuff. Our technique, our pipettes are really reliable and so on. Not so in a lot of the other scientific areas. Okay. So let's get into this correlation coefficient. We talked about the percentage of the scatter that the data, in the data that's captured by our model. And you want to definitely put a big circle on this page or some kind of star or some kind of indication, because you're going to have to use all of these equations in next week's homework. Okay. Spent all day yesterday doing all these little calculations. And so this is the least squares method, or the sum of squares method. You have these sums of squares here that are calculated based upon the X data and the Y data. If you do SYY, you just substitute Y values for the X values here. And then you have these down here. This Y bar here is just your average signal. And then the X bar here is just the average X value. So you just take all your X values and average them, and that's X bar. Okay. You take all the Y values and average them, and that's Y bar. And so this is pretty cool. If I just sum up all my X squareds, I square the X values and sum them, then I sum the X values and square the sum, divide by the number of X values, take that difference, that's the SXX value. Do the same thing for XY, where I have X times Y and sum of X times sum of Y, divide by N. And I get these sums of squares, and look, I can solve for the slope using just those sums. That's neat, okay? That's what's going on with the trend line. And then I can take those average values in the chart and solve for B. I can take Y minus MX and get B. So I can solve for M and B by hand. And so I want you to do that in your homework next week, just so you have an appreciation for what's going on. And you'll be able to enter those in Excel in the future to kind of do your linear least squares fits on the fly. You know, you don't have to do ANOVA all the time. You can solve for M and B and the uncertainty in M and B right there in the cells and not have to go through all those steps of doing the ANOVA. Now you need to do the ANOVA to get the P values for M and B, but in terms of M and B and SM and SB and calculating your uncertainties and so on, you don't have to go through the ANOVA or regression tool. You can calculate it yourself using these equations. And then R squared is this ratio of the XY term squared divided by X and divided by Y. So you can see how good your model is. So let's look at this calibration example. This first one is going to be the external standards. Then we'll look at the internal standards and then the standard additions. So external standards is the first method we teach you guys in chemistry. I'm happy to know that they cover internal standards and standard additions as well, but this will be a good review for you if you don't remember the details. You'll see this again, and I'll talk about it again, but I just want to mention again here at the beginning, internal standard is great. Say great. For reducing sample to sample noise. And then standard additions is for eliminating matrix effects. Because everything in your calibration is in the matrix, is in the sample matrix. So the first one, you're dealing with organic solvents or water and comparing that to blood. The internal standard is you're correcting for injector to injector variation. So sample to sample variation. And then standard additions, you're actually knocking out the matrix effects. And we will see that dramatically today. So let's do the external standards. First, we have an analysis of 125 parts per billion cocaine in blood. So this is sort of a test case. We know there's 125 parts per billion put into the blood. Now we're going to detect it with our calibration curve. So that's what's going on. So this is the first calibration. You learned the system must have minimal matrix effects for this to work well, but the sample is blood and the external standards are various amounts of cocaine in an organic solvent. So this is probably not going to match. But if it does match, it's real easy and fast and inexpensive, and you can run with it. So we're sort of evaluating, is this going to work? Calibrating with an external standard like this. The organic solvent is not blood, and so this may cause problems. So, so we'll see what those problems are. So here's our abundance of cocaine, parts per billion of cocaine, 20, 50, 100, 250, and 500. And so notice from our lowest standard, 20 to our highest standard, 500, they're really only changing 2 place values. So we really only have 2 orders of magnitude in our linear dynamic range. It is definitely linear though. That looks very nice. We have an R squared of 0.99. This is the peak area. So, on our chromatogram, we might have some, other things that come out, and then we'll say, okay, this peak right here is cocaine. And so we would set our integration limits, and we would tell the software to run all of these samples in our sampling tray and pull the chromatograms and integrate between these 2 limits and report the data in a table. And so a lot of this is automated. You load up the tray with your standards and your check sample, and you say go, and you've built this standard analysis method in the ChemStation software or whatever package you're using, and it will integrate those peaks automatically, produce an output table. It's fantastic. And so these are the integrated areas under those peaks. Now, that's just a signal from your detector. What is it detecting? Well, if it's a mass spec, you're picking a particular ion for cocaine. This could be maybe the total ion chromatogram. So these are all of the ion signals that are added together. But a lot of times the specificity that you get from mass spec is that you can pick a particular ion. And in that case, if you're just selectively monitoring the cocaine ion, you might just see just the cocaine signal. Or if it's a fragment, you might see a fragment from other molecules that fragment with that piece. Maybe a cocaine metabolite or something shows up too. But that's the nice thing of selective ion monitoring. So And this might be the total. So the signal from the total ions on the detector would be, you would get every peak. Selective ion monitoring would just be a peak associated with your analyte. So it doesn't say which one this uses. We just have the peak area from cocaine. Doing a ANOVA on this. So this is our independent variable. And this is Y, our dependent variable. Put those into the regression analysis. We get this regression output, which you're very familiar with from CHEM. And down here we have the intercept, which is B, and we have our cocaine signal, which is M. And we have our p-values, which again, that's a probability value. Can you state the null hypothesis for these p-values? Can anybody state the null hypothesis? Take a stab at it. And you can type in the chat too if you know it at home. I'll let you chew on that. Okay, so cocaine is the standard in a solvent matrix. This is our signal peak area from chromatographic signals. This is our linear model, y equals mx plus b. We have a good R squared value. Down here in our ANOVA output, that B is 12.1 or 1213 sort of area count. So the units of B are the same as the units of Y. You can see that from the linear model. M is the slope. So the units are always rise over run. So the units for M would be area counts per parts per billion cocaine. And then the uncertainty in B is 1504, which is kind of a problem, right? If you're looking at B, tell me what B is. Well, it's 1200 plus or minus 1500, right? So it might even be negative. Essentially, we have to say it's zero, right? If that contains zero, if your uncertainty contains zero, then it's not significantly different than zero. Even though 1200 sounds big, the uncertainty is so big that it could just might as well be zero. And then the uncertainty in M, we have M is 416 plus or minus 6. So that's not bad. So p-value is the probability that the null hypothesis is true. So what is the null hypothesis for those p-values? Notice that this standard error on B contains 0, and we have a high p-value. So those are connected. So you could say, is it possible? Is it the probability that B is 0? That's one way to say it, okay? But the technical way to say it is it's the probability that B is caused by random variation in the data. And so random variation in the data is giving us the number 1200. Okay, so it would be 0 if there was no random variation in the data. Why is it significantly different than 0? Well, the 0.47, we have a 48% chance that it is 0. 48% chance that random variation in the data, not anything related to cocaine and area counts, is giving us the number 1200. So we have no confidence in that number 1200. Because there's only there's a 47% chance, a 48% chance that 1200 is just the very time we ran it, we got, we drew a number out of a hat and got 1200. There's nothing significant about that number. So we could set it to 0 and actually improve things. Okay. Look at the M value. So that's the probability that M is 0, or not significant. It's one chance in a million that M is caused by random noise. And that makes sense if you look at that curve, that slope of that line, it really does match the data. And so if that line, if there's no scatter in the data that you can see and the line goes right through the points, you're going to have a significant slope. There's one chance in a million that particular value of M is just due to the random variation of our data. And so essentially, the simplest way to write that null hypothesis is that M and B are equal to 0, and that the numbers we're getting are just from random variation. So we have that high p-value. So what we'll do is we'll redo that regression analysis and we'll set the intercept to 0. Since it's not statistically defensible, we just need to set it to 0 and only model M. Okay, now here's where those uncertainty values come from in the ANOVA. So we still have the sum of squares values here. We have SX, X, SYY. Okay, this one is SXY. There's a mistake here in the notes. It's funny how I only notice my mistakes when I'm here in Zoom. SXY. Here's your M and B equations, but then here's SM and SB. So here's how you calculate the uncertainties in those numbers. You have to calculate the error or the standard error for the regression. And the only reason you calculate this is because it's needed in the M value and the B value. So you need that standard error for the regression in order to calculate SM and SB. So again, you can star this set of notes. You're going to use these equations in next week's homework. So we set that intercept to 0 for the trend line, and we also redo the regression analysis, setting that intercept to 0. And we'll see that some things have improved. So R squared went down, but that's really not a big deal. Okay, we really aren't as interested in R squared as we are the p-value. Okay, so look here, it was one chance in a million. Now it's one chance in 100 million. Okay, so we went to the p-value for our slope went down. So we've gotten a better statistical confidence in our slope, and it was 416 plus or minus 6, and now it's 420 plus or minus 4. So our uncertainty improved. That's fantastic. And so we take our 125 parts per billion check sample in blood, and we inject that, same procedure and everything, just a different matrix, just a different sample, and we get our check sample area. So this is 125 parts per billion of cocaine in blood. And so we can calculate that parts per billion. So we take that Y value and we divide by 420 and we get X. And so this is what we calculate, 68.2. So we put in 125 parts per billion, ran it on this beautiful calibration, external calibration, and we get something that is negative 45%. So our percent error is 45% low. So that's pretty bad. The precision of our particular analysis, though, is 1%. That's fantastic. We calculate this uncertainty using these uncertainty values in M. We don't have any uncertainty in our check sample because we just ran 1. I don't know why. We should have run 3 at least, but that's what we have. We're in a hurry, I guess. So here's our true value. We calculate that difference between our calculated value and the true value, and we find our percent error. Okay. And so this is saying the sample doesn't have cocaine. The sample has 125 parts per billion cocaine in blood, and our external standards were done with organic solvents. And so something's happening to that parts per bit, that cocaine in the blood matrix. It's probably those enzymes. So we have residual enzymes that are taking apart the cocaine molecule, and then that's showing up at a different place in our chromatogram. So the metabolite's showing up somewhere else, and the unmodified cocaine is coming in at 68.2 parts per billion. So that's what's happening to that extra 45%. So let's just show that propagation of uncertainty for that original model. Okay, so here we have, we're solving for X. We have Y minus 1213 divided by 417. And so we want to show where this uncertainty value comes from, this 3.7. And so we have X is equal to Y minus 112 and 3 over 417. And so we have a mixed, we have a two-part propagation. We have a difference on top, and we have a quotient. So we need to calculate the numerator. And that's going to be this 28,632 minus 1213. So can someone do that for me really quick if you have your calculator? I don't see any calculators out.
$27,419.
27,419. Okay, so that's the numerator. And now we need to calculate the S numerator. And so that's going to be the square root of S1 squared plus S2 squared. And S1 for this guy is 0. We don't have it listed. So we don't have anything listed. So this one is 0 in this particular case because we don't have an uncertainty with our check sample. But we do have uncertainty with this B value. So this is 1500 squared. And so we're going to 1500 squared, add 0 and take the square root. So it's just going to be 1500, right? So that's the uncertainty in our numerator. And here's our numerator value. And now we can calculate the uncertainty in X. And whenever you're doing quotients, it's the relative standard deviations squared. And so we have the numerator uncertainty, 1500 over 27,419. And that's where people make their mistake. They will put this check value in there incorrectly. Okay, this is the uncertainty in the numerator, not the uncertainty in the B value or the check sample value. Okay, and then the uncertainty in M. So we look up the uncertainty in M. We have 6 over 417. And the X was 65.8. Now I would take off 1 to 3 points for not showing any of my units on here, but then let's go ahead and put our unit here, at least for this. This is parts per billion cocaine. And so that gives me the uncertainty in parts per billion, including my units on here would give us in the denominator counts per parts per billion. And so then that parts per billion comes up on top, and the thing in the numerator is counts. And so that cancels the counts. So our units do work out. And this should give us the 3.7 parts per billion listed here. So that's how we're calculating those uncertainties. And next week's homework, you do this about 3 different times. Okay, so you should get some comfort in working through those. Now it's, you can download that test now. You can get started on it if you want, because it's like 26 problems of all these little pieces that you put in. Like you'll type in the M value and you'll type in the uncertainty in M and so on. So some of it's just reading the ANOVA table and knowing where to get those values. And then you'll have some calculations. What's the concentration? You know, what's the uncertainty in concentration? So, But if you get one of those wrong, then like 4 next ones are wrong. So you got to, make sure it all works out. If you enter your answers and you get them wrong, you got a couple of attempts. So you can go back and try to figure out where your mistake is. You can work together on that. Just make sure you do your own work, because you can't work together on the test. So our CV is 6%. That's pretty good. I mean, was what I say, that was fair. Okay, good was 5%, and excellent was 1% or less. The true value is 125, and so we're low, 47%. So this was the model that contained both M and B, and we did the M alone, and it was, again, 45% low. So both of these models were bad in terms of the accuracy, but they're pretty good in terms of precision. So I'm just showing again that propagation of uncertainty for the M value is a little easier. If we get rid of the B, then we just have this Y over 420. And so oops. And so just getting rid of that useless intercept improved our uncertainty. We were 6% CV here in terms of our precision, and getting rid of that B was actually distracting our propagation of uncertainty and giving us problematic values. So get rid of that noisy B value and look at our CV, it improved to 1%. So we have a good model here, but because of the matrix mismatch, it's just wrong. It's very precise, but it's not accurate. So let's do the internal standard method. I'm kind of telling you it's due to the matrix effect, but maybe it's just sample to sample variation. This is how we would get rid of sample to sample variation. So our blood versus organic solvent is a matrix mismatch, but we can see if we can improve our analysis by adding in another standard, not cocaine, to each aliquot. And so we're going to put the same amount in each of our aliquots to provide a ratio signal. Now this requires a selective instrument, but that's one of the strengths of chromatography. You can have lots of analytes in the same sample and it separates them and analyzes them. So that's what selectivity is. It can just tell the difference between the different analytes. Infrared, straight infrared is not very, it can be selective, but it's not nearly as selective as the separation technique. If you put a mixture on the infrared, you're going to have all those peaks on top of each other. Now it's somewhat selective because the peaks are narrow, and you could find a peak associated with substance 1 and a peak associated with substance 2, but not always. And so if you could separate those substances, then you would definitely have more selectivity. And so what we do is we put in an amount of xylocaine. This is sort of related to cocaine, but different. And notice that we put the same amount of xylocaine in every sample. So we redid our calibration, 20 through 500. We get peak areas for that. We put in 75 parts per billion of xylocaine in each standard. And so that signal in an ideal world would be the same. We put the same abundance in, and we should have the same area counts out. And look at the changes. It's changing in the second significant digit here. I mean, they're all 30,000, but there's quite a bit of variation here. If there was a 3 from 1 to 3 in the second digit, that would be a variation of 10%. It's not quite 10%. It may be 6.7%, because we go up to 2 at least on this one. So we're looking at 6% variation just sample to sample. Now, most of our injectors in commercial labs are auto injectors. And so the little robot comes and puts the vial in there, and this auto sampler grabs the syringe out and goes and injects it in the instrument. And that has improved this precision greatly, because the hand injection was one of the largest sources of error or uncertainty or precision problems in these analyses. And once we got rid of the analyst's technique and jabbing the needle through the inlet and squirting the sample into the inlet, if they did it slower, more evaporated, the peaks were spread out and so on. They did it really fast. They might get more of a concentrated signal. So this peak area goes all the way back to how you inject the sample. And we went to auto injectors and really improved the situation quite a bit. Now, I don't know if this was using an auto injector. Probably was, because I think even hand injection would have varied quite a bit. And you can have this internal standard be all over the place, but because we take a ratio signal, when you have a really strong injection like here, then that signal is going to be reduced a little bit. When you have a weak injection, you're dividing by a smaller number, and so it's going to boost the area counts up a little bit. So the ratio signal is going to be scaled by the internal standard, and that's what we're calling this area ratio. And so that's our y-axis now. We have peak area relative to the internal standard versus parts per billion cocaine. And we have quite a different model. Now our M and B are really small numbers, but that's irrelevant. And so here's the regression analysis. Once again, our intercept is not statistically valid. It's got a p-value of 0.4. So that's greater than 0.05, which would be our cutoff for 95% confidence. So our calculated parts per billion of cocaine is 126. Hey, that's not bad. You know, we put in 125, we got 126. Our uncertainty is 3.1 parts per billion. So it's precise, you know, it's 2%. So that's good precision and excellent accuracy. So that is really great. Internal standards fixed it. Okay, even though we thought it's a matrix mismatch, and it is a matrix mismatch, but it looks like it was injector to injector variability that was causing us to be so low. Now, I don't exactly know how that could cause us to be low, but this fixed it, or appears to fix it. And so here's our confidence, our 95% confidence limit. So 1.96 times our uncertainty gives us that 5.9. And so our lower 95% confident value is 120, our upper is 132, and those contain the true value of 125. So that's fantastic. But does that B value bother you? Right? This isn't statistically defensible. So let's redo the analysis, setting that intercept to 0. Yes.
Sorry, what are the 5.9?
Oh yeah, good question. So this uncertainty here, so 1.96 times the 3.1 gives us that plus or minus for the 95% confidence. So great question. And then I just went ahead and put the upper and lower limits so that you can see what that actually means. It's plus or minus the 5.9 or plus or minus 6. All right, great question. So then we set that B equal to 0 and redo the regression. So we get a new check sample area, a new internal standard, and we take the area ratio. And now we're calculating 127 parts per billion. Our uncertainty improved greatly, 0.9 parts per billion. So now our CV is 1%, but the true value is 125, and our percent error is 2.1%. So we've gone from excellent accuracy now to good accuracy. And we're kind of bothered because our uncertainty improved so much that this times 1.96 gives us a plus or minus 2. And so our 95% confidence interval does not contain our true value. So this is uncomfortable, right? We changed things to make them more statistically defensible, and now our check sample is off with biased high, 2%. And our precision is such that that's significant bias. It's putting our check sample, our 125, outside our confidence limit. So this is uncomfortable, okay? So let's wrestle with this. You know, we've got a dilemma. The statistical values improved. So our p-value for M went down, again, from 1 chance in a million that it is randomly generated to 1 chance in 100 million. We got rid of the useless B value, but the accuracy got worse. So what should you do in this case? And notice I'm using the word should. Should is moral language. This is the is ought dilemma. Science will tell you what is, but it won't tell you what ought. That's where we bring morality into the picture. So when you say, what should you do? We're making a moral claims. We're discussing ethics, right? And the only ethical case we have here is to go with the statistically defensible answer, right? Because otherwise you're letting your bias manipulate your actions. You know we want that check value to be within our confidence limits. And so if we were to choose the non-statistically defensible position, we're letting our bias change our decision, and that's bad. So we have to go with the statistically defensible model, even though it puts the true value outside of our limits. And that's leading us to ask more questions. Maybe the matrix is a problem. And so then we'll do standard additions to show, yes, the matrix was the real problem. But this is just time to sit back and think about what we're doing. We're analyzing data, and simple decisions like this are ethical decisions. And so we need to be aware of that. You know, this is a long way from the courtroom, but this is where ethics, the rubber hits the road, when you're deciding which model to use, what to write in a report, and you have to go with the objective data, not your personal desires. We had a situation in one of my previous jobs where there was it was an accident, but it wasn't an accident that caused any trouble, but it was something dangerous, and we needed to analyze what happened. And so we had a lot of people on the team analyzing what could have happened, what should have happened, and so on. And my boss asked the person that was presenting the results of their study, you know, question after question. Finally, he said, "These are some strange calculations. Why did you do these calculations?" And this person said, "Because it gave us the answers we wanted." And he dropped his head, and I mean, it was quiet for minutes. And I was so like, and he said, "I cannot believe I heard that." You know, he was so disgusted at that. Do the appropriate calculations, not the calculations that give you the answer you want. We want that true value to be between our limits, but we can't let that desire make us do calculations that are not statistically defensible. So let's do standard additions. This is where we take the actual blood sample and break it into 4 analysis samples. So we put 125 parts per billion in the blood, and then we break it into 4 aliquots. So this is the actual matrix, and then we add in some more cocaine. We start with 0 on one of them, we add in 0, and then we add in a little bit to the 3 other samples. The problem with this is it requires enough blood sample to make 4 or more analysis samples. And it's destructive in the sense that you're consuming. If that's all the blood you have, it's gone. Blood, typically, I don't know, you can imagine that you have about 5 liters of blood in a person, so you might have quite a bit of blood, but ocular solution, you know, there you might have a problem with the ocular matrix. I mean, you might not have a problem with urine or blood, but for something like the vitreous fluid in the eye, you might not have enough for a standard additions set of samples. But you know, if you're dealing with GC and you're dealing microliters, maybe you will. Okay, and so then this is the interesting part of standard additions. This time we solve for the x-intercept, and the x-intercept gives us the initial amount of cocaine that's present in the blood. And so we'll see that in the analysis chart. So here's our 4 blood samples up in the top table. We've added additional parts per billion of cocaine to these bloods of 0, 50, 100, and 200. And then this is our plot, and it's so good that the R squared is 1, which just means it's like greater than 0.99995, right? 5 or more. And that'll cause it to round up to 1. You know, I'm sure it can calculate it. It's just that the 9s go out more than 4 decimal places. So we got 4 9s or better. Well, I know we have 4 9s. And so then this x-intercept, you see it doesn't go down to 0. It's somewhat negative. And so if you were to extrapolate this line down to where it hits the x-axis, so the x-intercept is where y equals 0, then notice it's a linear trend that didn't start at 0. We added 0 additional cocaine here, but there was already some present. And so because there was already some present, then the signal comes up here and hits, you know, at 30,000 or something, even though we didn't add any additional cocaine. So this initial signal is from the initial amount of cocaine that was already present in the blood. And so here's how we do this. We get the regression output, and notice our intercept and our parts per billion, our intercept and our slope are fantastic p-values, 10 to the minus 6 for both of them. And the equation too is different. So this is our model, y equals 240 x plus 30,000. And so solving for x, we set y equal to 0 and solve for x. And so it's y minus the 30,000. So don't drop that negative sign. That's your number one place which you're going to screw this up. Is to not drop, is to miss that negative sign on B when it moves over to the other side of the equation, and then you divide by M. And our calculated parts per billion is 125.42. So that's a good start. Our uncertainty is 0.23 parts per billion. And so that's a 0.2% coefficient of variation. And then our check value, of course, is 125. And our accuracy is 0.3%. So it's excellent accuracy. And our 95% confidence, this 0.23 times 1.96 gives us 0.46 parts per billion. And that goes from 124 to 125.8, and 125 is right here in the middle. Isn't that beautiful? So again, it was both an internal standards problem and a matrix effect problem. The internal standards fixed it one way, the matrix effects or standard additions fixed it a different way, and the standard additions is better because we're dealing with blood that has enzymes in it that takes apart our analyte. And when we put in our standard additions, it takes apart that analyte too. And so that's why this is so good. Precision and accuracy are good because we have the same matrix for our standards that we do for our check sample. So that's a lot of information. We went through all 3 different types of calibrations, or the major types of calibrations. We hopefully have made you more comfortable looking at the ANOVA output. And if that p-value is greater than 0.05, then you have to redo the regression and get rid of the intercept, or look at your model. If the M value doesn't have a p-value under the 0.05, then you've got a problem with your instrument. Your signal is all over the place, or your technique is so bad, you know, instead of pipettes, you're just dropping in 2 drops and 3 drops and 4 drops. Yeah, pipetting by mouth and spitting it out, you know. Something's wrong if your M value, if your slope is not statistically significant. You know, that's almost never the case. It's the intercept that you have to worry about. Hopefully you're comfortable with the propagation of uncertainty. Definitely go back through these notes and make sure that you're comfortable with that, because that is a huge skill. That's the ninja skill. A lot of people can do average and standard deviation, right? But if you're able to propagate the uncertainty and always report a number with the level of uncertainty, your bosses are going to notice. Let's see, what do we got? What does getting rid of the intercept mean? Okay, so that's a great question, and we've got enough time. Let me pull up Excel. So let's let me just run this just so I can get Excel open, and then I'll open a new sheet. Yeah, okay, I don't know what that means. All right, so. Okay, so I've got to generate, we've got 10 minutes. Let's generate some data. So we've got X, 10, 20, 100, 50, 500. Okay, and then Y values. What is this? It's, the arrow keys are tied to panning the screen, not to moving it. Scroll lock. Yeah, okay, let's try that. Yeah, okay, that was it. Scroll lock. That's strange. So Y. Now I'm gonna give it an M and V and some noise. Okay, so we're gonna say Y is equal to 1,000 plus, we'll say we'll have a slope of 300 times random number times my X value. Okay, so I just put random number in there so that we get some noise. Copy, and we'll just double click that corner. So I'm going without a net here. I've never done this. I've not done this publicly before. I do this in my office all the time. So we're gonna do a chart, scatter chart. And so there's our data. We'll do a trend line. More options so we can show the display equation and display R value. So there we are. And it's not so great, right? 99.15, we got a funky data point there. But what I'm going to do is I'm going to copy these now and I'm going to paste values because I don't want to, if you, I'll show you, if you hit F9 or anytime you make a change, the random number generator changes. Right, so let's pick one that's kind of suspect, like this one. And I guarantee that B is going to be no bueno. So, and then we'll paste values so that doesn't change every time we make a change to the chart. Oh, okay. Well, once I paste values, it changed, but now we've got one, and that's a pretty ugly regression. So let's go ahead now and do our regression on this. Again, the question in chat was, what does it mean to get rid of the B value? So data analysis tool. This is great for the video. This is going on YouTube. Regression analysis. So our input Y range, I don't know why they put Y on top. I always think of top one should be X. X values. To answer your question directly, click this means take out the B value. So setting that constant to 0, that is getting rid of the intercept. But we'll leave it in for now. We're going to pick an output range here. We click in that cell and we're going to click right there. So that's where it's going to put the regression output. Okay, and we hit go, boom, there it is. So p-value for the B is garbage, right? Because I put that random noise in there and it's messed up the B value. So we don't like this. And not only that, look at it, it's coming in negative, okay? And so it's negative 6,000 plus or minus 7,000. Not too confident in that number, okay? But the M is, it's 0.007, so that's okay. It's not the best, but look at R squared. It's only 0.99, 0.98. So what we mean by get rid of the B values, we do the data analysis again, and we just check that box, okay? And that's what I mean by getting rid of the intercept. So you check that box to set the constant to 0, and then we give a new worksheet ply here. So we're going to tell a new output range, and I will put that right here. Okay. It's going to overwrite some of the data, but that's all right. We'll get it down here next to each other. So our p-values for the we got another order of magnitude on our p-value. Our slope went from 300 to 293, plus or minus 27 was, or now it's plus or minus 20. And our R-squared values, let me skip those over, went from 0.98, or it was 0.984, now it's 0.985. So R-squared is really not the best tool to use to decide between models. It's the p-values that you would use to decide between the models. So that's, if you ever want to fake data, I mean, I just taught you how. Rands, open, close. I mean, that's all you got there. Again, science tells you what is, not what ought.
Moral question.
That's a moral question. That's an ethical question. Yeah. So don't do it. All right. So that's good for today. Great question, Aurelia. Thanks for asking.
Please, Jeff.